Okay, so I will talk about witness encryption. This is a primitive that was suggested about a decade ago, and essentially it is an encryption scheme where you can take an instance of some computationally hard problem and say that you encrypt the message with respect to it in such a way that only if someone has a witness that solves this problem, then they can decrypt. And otherwise, if there is no witness, then it is impossible to decrypt. So it is useful in cases where, for example, the encryptor himself does not know if some computational problem is feasible or not. So they can say, I have this prize for someone that might in the future be able to solve it, and then I encrypt the message with respect to the problem. And if in a few decades from now, someone will manage to compute the solution, then they can use their witness and automatically they will be able to decrypt. So a syntax of such a scheme is relatively simple. The only thing we have is an encryption algorithm. So the encryption algorithm, and of course a decryption algorithm. So the encryption takes the message that should be encrypted, and in addition, a verification algorithm that takes a witness and then either accepts or rejects it. And the decryption should work only if someone presents a valid witness for this verification algorithm. And otherwise, if there does not exist a valid witness, then the decryption should be hard for everyone. So there are no additional decryption keys, and there is no interactive security game or anything of this sort. Yeah. So since the introduction of this model, there have been a few attempts to come up with candidates. So there is one candidate with provable security for multilinear maps. And a few years after that, a few additional candidates were suggested from lattice-based assumptions, but we do not know how to analyze their security. So they are there, we believe that they are secure, but we do not know how to prove that. And of course, with the recent advances of I/O, we can use I/O to also derive witness encryption, but then we need to go through a really long line of reductions, and we lose the intuition about the security somewhere along the way. So it is still interesting to try and come up with a scheme that is simple in some sense, so we can better understand why it is secure. And even if we don't know how to prove it, we can still point out the missing piece in the puzzle and say, this is the only thing that we need to prove in order to show that this is secure. So this was our motivation. And we suggest a construction from lattice assumptions, and we also can analyze its security, and we can prove that it's secure under a new assumption, which turns out that is not new, because at the same time, Rotem came up with a very, very similar assumption that he just discussed in the previous talk. And actually, we see this as an encouraging thing, because it means that first, other people think that this is something reasonable to assume and try to think about it. And second of all, it means that the assumption is not too specific for our construction and has other applications like the broadcast encryption that Rotem showed. Okay. So the computational model that we will use is a branching program. So in a branching program, we have evaluation steps that should be applied sequentially. And we sometimes also call them levels. And in the first level, there is a state that is defined to be the start state. And in the final level, there is a state that is defined to be the accepting state, and all of the other ones are rejecting. And then in each step, we have two mappings, one mapping for 1 and one mapping for 0. I denote them here by blue and orange. And in addition, there is a definition for each step of the evaluation, which bit out of the input bits should be read. So in each step, in order to evaluate the program, in each step we would have to look at one of the input bits, and depending on its value, we either apply the zero mapping or the one mapping and move to the next step. Yeah, so just as an example, if we have an input of length 4 and we need to read its bits 7 times, so we can each time take one of the mappings according to the bits, and then we would end up with some state, and here we ended up with a rejecting state, so the output of the program should be 0. And if we were to end up in the accepting state, then the output would be 1. Okay, so according to Barrington's theorem, in fact, for every function that can be computed in polynomial time, we can express it as a branching program of polynomial size. So yeah.
You don't care about fixed width, right? You can.
Yeah, as long as it is the number of nodes is polynomial, it's fine. But
log space. Like if you don't care about the width, then it's easily captures log space, which is.
So we will use Barrington branching program, so we can assume that the width is fixed to 5, and then the length is polynomial. Okay, so now assume that we want to design witness encryption based on a branching program. So as I said earlier, the only thing we have to work with is the encryption algorithm. And we need to somehow exploit the structure of the branching program in order to have this mechanism that you can only decrypt if there is a valid witness. So we need to somehow make use of the starting node and somehow make use of the end node. And then because the encryptor itself does not know what is going to be a valid witness, we also must provide some flexibility for the decryptor to choose how to evaluate the machine. So it needs to be possible to either take the 0 mapping or the 1 mapping for each and every step. So a reasonable high-level approach would be to somehow define one part of the ciphertext that is associated with the starting node, another part of the ciphertext that is associated with the end node, and then for each step to provide 2 keys that allow to either take the 0 mapping or the 1 mapping. But recall that when we come to now analyze the security of a candidate that has this structure, then the only assumption that we have as the prover of the security is that there does not exist any valid witness. And when we translate this assumption to the structure of the branching program, it means that the only thing we have to work with is the fact that there is no valid path from the starting node to the accepting node. And the problem with this assumption is that it is not true, because we know that there are no valid witnesses, but there might still be some paths from the start node to the accepting node, but it will not satisfy the rules of which bit should be read at each step. So, for example, here we have an input sequence that violates the rule of which bits should be used, because the first and the last bits should be identical, but it still results in a path that is accepting. And if we give the decryptor the flexibility to take the mapping that he wants in each step, then he can use this kind of attack to eventually decrypt. And just as a side note, actually in branching programs that do not have this kind of reading the same bits multiple times, it's actually trivial to get witness encryption, because the encryptor himself can apply BFS or DFS from the starting node, and if there exists any path from the starting node to the accepting node, we can translate it to a valid witness, and then it becomes trivial to encrypt. So this is the challenge, and this is the only interesting challenge that should be faced.
So you're saying satisfiability is trivial, then so is witness encryption. Satisfiability for F is trivial.
Yeah, as an encryptor, you can check the satisfiability, and if there is a witness, you put the message in the clear, and otherwise you output nothing. Yeah, okay. So to overcome that, our starting point is a generalization of a branching program that was suggested by Chen et al. And it allows to detect when the program is evaluated with inconsistent sequences. So the generalized model considers a branching program that instead of holding a single state in each step, it starts with multiple steps. And then whenever we take an evaluation step, we need to update all of these states simultaneously, either according to the 1 mapping or to the 0 mapping. And then after we apply that, so we will also end up with multiple states. So there also should be some rule that defines, takes as input the vector that represents the output, the last level, and then either accepts or rejects it depending on the active nodes. So given this generalization of a branching program, we can now apply a consistency checking in the following manner. So the way I like to think about it is that for each bit of the input, we add additional component to the branching program that takes care of verifying that one of the input bits is applied consistently. So I will not go into all of the details, but it is relatively simple. But in high level, we can, for example, if you want to have a memory cell for the second bit, so we can add 4 additional states. One of them represents that this bit was not read yet. Another one represents that it was read and it was 0 every time that it was read. The same for 1. And the last state denotes that it was inconsistent. And then we can define the mapping rule such that they always keep satisfying those 4 states. And eventually we say that as long as we didn't go to the inconsistent state, then we can accept, and only if we were inconsistent, we reject it. So now given a standard branching program, we can concatenate to it all of these memory cells, 1 for each input bit, and we end up with this slightly larger branching program. And for each of the components, we have the rule whether it accepts or rejects. And now we need to have one final rule for this concatenated program. So we will simply say that the large program accepts if each of the components accepted the evaluation. So just as an example, if we have a valid a sequence that is consistent with some input, then all of the memory cells will accept. And if we have a bad input, then the bit where we're inconsistent, its memory cell will detect that and reject. So now let's get into the lattice techniques that we're going to use for the construction. So we're going to use a variant of GGH15 encodings, and this is essentially a way to generate lattice problems according to a structure of a directed graph in very high level. So suppose that we have an example directed graph. We will associate with each node some public matrix, and for each edge, some LWE secret. And then there is an encoding algorithm that works for an edge. So it takes as input a trapdoor of the source matrix, and it takes the target matrix. And in addition, it takes the secret that is associated with this edge, and it outputs something that is called an encoding for this edge, respective to the secret that we defined for this edge. Now, the nice thing about these encodings is that they have 2 properties. First, they allow to convert an LWE instance with respect to the source matrix to an LWE instance with respect to the target matrix. But the other property is that they also leave some trace that remembers the edge that we use. So for example, here we have two possible paths from A to B, and depending on the encoding that we chose to use, we will end up with different secrets for the LWE instance with respect to B. So this idea was applied on branching programs for multiple use cases. In some of them, we know how to prove security, and in some of them not. So it was mostly used for variants of candidates of IO, but also for constrained PRF. So how would this be applied on a branching program? We will associate each node with a matrix. So there should be more matrices here. I just didn't want to overload the slide, but every node would have some matrix associated with it. And we denote the starting matrix by A and the accepting matrix by B. And then for each evaluation step, we also sample two LWE secrets, one for 0 and one for 1, and we associate each edge of each level with the secret that corresponds to its mapping.
So, Rotem, the M's are random matrices.
So they should be sampled with a trapdoor, so you can compute the encodings, and in the last level, TBD. I mean, yeah. Generally, yeah, like here is like a general use case, so B would typically be random, and all of the other matrices should be sampled with a trapdoor. Okay. So now, in order to compute an encoding for a branching program, we will provide an LWE instance with respect to the starting matrix, and then for each edge, we will compute an encoding like we saw before, respective to the secrets that are associated with this edge. Yeah, so now let's say that we have this encoding and we want to evaluate the branching program. So we start with the LWE instance of the starting node. And every time we want to apply one of the mappings, we use the appropriate encoding. So the K that corresponds to the bit of this step. And it has the property that if we multiply them sequentially, then this trace of the secrets will add up, and we will end up at the final state of the program. So here I chose a path that goes to the accepting state. So we end up with an LWE instance with respect to B. And of course, I assume that there are error terms here. I just didn't try them. But then we also have this memory that remembers which path we chose in order to get to the accepting state. And it turns out that actually, even though these terms of this form are highly structured, they actually have a lot of computational entropy, and they can even be used as a PRF. So even though we always use here the same B matrix, the fact that we have here a different multiplication for every X is enough to state that terms of this form look random. Of course, if there is an error here, if we see them for multiple X's. Yeah.
Sorry, maybe I missed something. So how are you checking for inconsistency of input here?
What?
How are you checking for inconsistency of input here?
Yeah, so I didn't get to that yet. This is just an example. This is actually the Encryption PRF. Just an example on how to apply encodings on the branching program. Okay, and also note that this is just a standard branching program. It doesn't have the multiple active states. Great, so now let's try to apply a similar idea to a state that has multiple active states simultaneously. So this is the branching program that we saw earlier. So now, for every starting node, we will associate it with some matrix. And in the output layer, we sample matrices in the following way. So recall that we said that the machine accepts the output only if each of its components ending in an accepting state. So this can be thought as an end of ORs, right? For each component, we have an OR condition, and then eventually we have an end condition over all of them. So we can apply an information theoretic secret sharing according to this formula. So for each component, we sample a random matrix and tie it to each node that is accepting. And eventually for the last node, here it is first, but for one of the components, we define its accepting state to be associated with the sum of all of the other matrices. Okay. So now the encoding will be an LWE instance with respect to each of the starting nodes, and also an encoding for all of the edges like we saw in the example earlier. So what does this structure give us? So intuitively, we can now start from each of the starting nodes according to our choice, and we can also choose any evaluation sequence that we want. And then we will end up in one of the output states. And if we end up in a rejecting state, so assume that this is just a random metric, so this is not interesting. And if we end up in an accepting state, so we will get a term that has the matrix B of the accepting state with the trace that remembers the path that we chose to evaluate.
So Rotem, 1 second. So if you set B sub f to be the what you wrote plus B.
So there is no B here. Here there is a B because I meant like either of those B's.
Sorry, say again. Please say again.
So there is no B matrix here. Without an subscript. Yeah, exactly.
So, but I guess what I'm saying is, if there were a plain B matrix, right? This would be a constrained PRI, right? So if everything checked out, you would get the product of S's indexed by X times B. That's the output of the PRI, right? Otherwise, you won't. Something went wrong. Either you were not consistent, or you were in a reject state.
But then where would I put that B in terms of associating it with
so the matrix B sub f would be B minus the sum of B sub j.
Right, so right now your B is 0.
That's right.
Yeah,
that's right. Exactly. That's right.
Exactly. Thank you. Yeah. So it depends on the application that you want.
Yeah. Exactly.
Okay. So. Yeah, so I didn't say, but the encryption would be, the witness encryption would be to either provide the sample or to give a uniformly random vector, depending on the bits that we want to encrypt. So before I go into the security analysis, which is the longer part, let's see the correctness. So suppose that I have a valid witness, so I can use the mapping that determines the evaluation sequence that corresponds to it. And then I can evaluate the machine, and because it is consistent, then each of the memory cells will end up in an accepting state, and also the component that evaluates F will end up in the accepting state. And then I get an LWE instance, both with respect to B and with respect to each of these matrices. And because when they are summed up, we end up with 0, we can sum up all of these terms. And then depending on whether this was an actual LWE instance or not, we will either get something uniform or something small, and we can learn what was the encrypted bit. Okay. So for the security, so before we go into the structure of the proof, let's analyze all of the possible cases. So let's think about an evaluation sequence that is consistent. It does not violate the consistency checks. It is consistent with some witness. So we know by the assumption of the security that there shouldn't be a witness that is accepted by the machine. So it must be the case that the first component that actually computes F will end up in a rejecting state. So even if all of the cells are accepting, here we will end up in the rejecting state, and we will not be able to derive an LWE instance with respect to BF that also has a trace of this sequence X. So this is in case where we were honest and using a consistent transcript. Now let's assume that we're trying to trick the machine and use a sequence that violates the consistency. So there must be at least one index J where it is inconsistent, and therefore its memory cell will end up in the rejecting state, and we will not be able to compute an LWE instance according to the matrix of this memory cell, also with a trace of this transcript X. So in either case, no matter which transcript we use, we can never manage to get LWE instances with respect to all of the matrices that all have the same trace of evaluation sequence. Okay, so yeah, before I go into the analysis, I just want to say why intuitively this should be secure, because we saw earlier that this structure of S values adds a lot of pseudo randomness, and in fact, even if all of the B matrices were identical, if we could only see one instance of them, then these values would look uniformly random. So even though we see here multiple values according to the same transcript, as long as they look uniformly random, this should be fine.
So, yeah. The GTH15 keys, right? The what you put in the arrows, the recording keys, they are correlated. So, or rather, you said A to B, right? Now you're doing many A's to many B's, and those B's are actually correlated, right? There's B1, 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 blah, 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 right?
That's why I cannot prove security using the standard technique.
Right, right.
Yeah,
and that would be true even if you replace the B sub F by the one that we were discussing, you know, B, the random matrix B minus. Still, it won't be. It's not obvious.
True. As long as all of the matrices of the next level are somehow correlated, you cannot apply the standard analysis. Yeah.
Right.
But the intuition says that because for each secret we can only see a subset of the matrices, and those are not correlated, then hopefully we can believe that this is secure. Okay, so now let's see how to analyze this. So let's go back to the toy example we started with of the GGH encoding. So typically the analysis would take the following steps. So if B is a random matrix, we know that LWE with respect to it is hard. And then it is not trivial, but it was shown that we can simulate the encodings instead of using the trapdoor of A. And because we no longer need the trapdoor of A, we can sample A uniformly at random instead of generating it with the trapdoor. And then now we can say that also LWE with respect to A is hard. And if A had more predecessor, then we could apply this argument again and again, depending on the structure of the graph. So in the standard branching program, we can apply a similar argument as long as all of the matrices here are random. So we can say that LWE with respect to B is hard because it is generated without a trapdoor and they are uniformly random. And then because of that, we can simulate the encodings that were used to point to it. And now we no longer need the trapdoors of the previous level, so we can also generate it uniformly at random. And then we can apply it again and again and again. So we analyze the machine from end to start. And then we will end up with the start level that is also uniformly random. And we can say that LWE with respect to A is now hard because A is without a trapdoor. So this is the standard analysis methodology. But now let's go back to the construction. We cannot apply it here because the matrices here are correlated. So we cannot state that LWE with respect to the matrices here is hard, because it is not. But we still have the intuition that we had earlier that, in fact, the attacker can never see an LWE instance with respect to all of these matrices simultaneously. These are the cases that we went over earlier. So let's take this intuition and define an experiment according to it. This would be our first step in the analysis. So we define a special LWE experiment. We have an oracle that has all of the values related to the system hard-coded to it. So it has the initial secret, and then also each secret that is associated to each level of the program, and also has all of the output matrices. And then we have an adversary, and the adversary can send a transcript of his choice, and you will receive back an LWE instance with the trace, the secret trace that corresponds to this transcript, and then only output B matrices that can be accessed according to the branching program. So if this transcript is consistent for the jth bit, he will receive the LWE with respect to Bj. And if this transcript leads to the accepting state of the component that computes F, then he will receive LWE with respect to Bf. And assuming that there is no valid witness, like we saw earlier, it means that he can never receive an LWE instance for matrices that are correlated.
So this is an experiment that knows the branching program, right? The oracle knows the branching program.
Yes, because it needs to be able to compute that.
Yeah.
Yeah. So this captures the intuition on why we believe this should be secure, right?
So in a sense, you're saying the only way I can try to decrypt the witness encryption is if I try a witness one at a time.
A transcript one at a time.
Yeah.
Yeah. Okay. So in fact, if we assume that this is the security game, we can prove from standard LWE that this experiment is hard.
Like that you can distinguish this from uniform?
Exactly, yeah, that the adversary cannot tell whether he receives uniform responses or from this distribution. And so we can prove that this experiment is hard, but the proof requires a unique hybrid for every evaluation sequence. We handle them one by one depending on whether they are consistent or inconsistent, and then we end up with exponential number of hybrids. But I just want to point out that the original works, that both the one that suggested the notion of witness encryption and the one that suggested a construction for multilinear maps, so in their construction, they also require exponential number of hybrids, and they gave some reasoning on why it should be the case. And the reasoning is something along the lines of, if we had an efficient proof, then we could use this proof to decide the language, more or less. It has some asterisks, but it does match the same challenges that they had in the proof.
But in this experiment, the adversary is submitting queries, so it's more like a PRF experiment instead of not knowing where to see experiment.
As opposed to what? It's like a PRF. It is sort of like a
PRF experiment, right? But
yeah, yeah.
When I ask for polynomial number of X, then you know what are the instances
So the heuristic, in some sense, implicit here is that the only way I can try to use the witness encryption is by evaluating it on a polynomial number of points, and that's.
Why does the reduction still need to run exponential time if you are in more sort of the PRF experiment?
I see.
So the oracle depends on the function f, and if you could find an input on which it outputs 1, on which it accepts, then you could easily distinguish. So somehow to be able to argue that you can distinguish, you kind of have to know that there's no There's no input on which it accepts.
Yeah, but I guess Rachel's point is that you're only getting these answers in response to particular x's, and I can only query polynomially many x's. So why do you need exponential? Right?
Yeah,
If the adversary was sending the instance, the witness encryption instance, then it's a different story, right? But
yeah, the adversary did not see the witness encryption instance. It sees the output for any particular X that you can obtain. And he can only ask for polynomial number of them.
Yeah, so we define this experiment, and then we can show that this experiment is hard in the case where there is no valid witness. But now we also need to somehow claim that the original security game against the actual encryption is equivalently hard as this ideal experiment. So yeah, this is where we did an assumption. So we want to prove that the witness encryption security game is as hard, or at least almost as hard as the experiment we just defined. And this is where we show the new assumption, which is extremely similar to Patrick's evasive LWE assumption, which essentially says that the only thing that the adversary can do with his encodings is to evaluate the branching program from start to end, and the fact that he has these encodings that does not give him any extra leverage beyond using them as they are supposed to do. So this also can be thought of as a semi-honest security of the trapdoor samples. So the way we phrase it is that, again, this is a simplified version of what appears in the paper, but suppose that we have a matrix A and a matrix B and a trapdoor sample from A to B. Then the game where we have LWE with respect to the matrix A and we get as auxiliary information this trapdoor sample is at least as hard as an LWE experiment with respect to the matrix A and B, and where we don't get the trapdoor sample. So in Rotem's assumption, he said that if this game is hard, then this game is hard. And here I need something slightly stronger, which is that this is at least as hard as this. I don't know yet whether this is hard, so I cannot assume in my proof that this is hard and then use it in order to claim that this is hard. The only thing I can claim is that this experiment is as hard as this experiment.
What does that hard as mean?
What?
What does as hard as mean?
What is what?
What does as hard as mean?
So the way it is formally defined is that for every adversary with some advantage in this game, we have an adversary with some advantage in this game, with similar advantage in this game, plus some negligible.
So you're also looking at the indistinguishability to pseudo-random.
Yeah,
So,
exactly.
So it's the other way around, right? Unless I'm missing something. If there's an adversary that breaks the left guy, then there's an adversary that breaks.
Oh, yeah, all right. Yeah. I mean, the other direction is trivial, right? Because if someone breaks that one and then we get this kind of challenge, we can apply the trapdoor. Yeah. So then we apply this assumption from the beginning of the branching program towards the end of it, and recall that the real ciphertext includes LWE sample with respect to the starting nodes and then all of these encodings. And then in each step, we apply this assumption and we replace the encodings of one of the evaluation steps with the matrices that the adversary could access if he were to use them on all of the LWE instances that he currently has. So we apply this for each step, and then eventually we end up in a game where the adversary has no encodings at all, but now we can access exactly all of the states that he could access as we defined in the experiment in the previous slide.
So you know, like this is a formal statement here is that for every adversary that breaks one, there is an adversary potentially with a larger runtime that breaks the other.
Polynomially.
Polynomially, right? So if you sort of repeat, you're probably going to repeat it for every sort of step of the branching program, right? So now the runtime of the adversary potentially blows up, right? At the end. So like, but that's
overhead, and it's okay.
Yeah, but I do not apply it for every starting matrix and edge. I apply it just for every encoding. So you can hack it depending on how you define the assumption, right?
Even for every encoding, you have many layers. So it depends on how you do the hybrids. So there's at least one hybrid per layer.
Yeah, I mean, I guess what you were asking is that if he already has access to many matrices, and now we apply the assumption for each source matrix and each edge, then it grows exponentially.
Right,
That's
right,
what you
right,
meant. Yeah.
right.
So the way I phrase the assumption is that because I assume that even if he has this oracle access to many matrices, he runs in polynomial time. So, and because this is an experiment, I guess, an oracle, then he can only apply the trapdoor polynomial times in each step. So the way that the assumption is phrased is again as an interactive game against an adversary, because I never want to assume that he has as actual inputs all of the LWE instances here. It is always formalized as a game against this oracle. And then I assume that the cost of applying an encoding is similar to one evaluation step. So this translates to one query to the oracle.
So the proof applies this assumption. Then it applies the assumption related to the oracle assumption.
Yeah.
Alternately, is that?
No. So this is the overview of the proof. So we start with the real encryption, and then we first apply the assumption for all of the steps. And in each step, actually, we have this model of LWE oracle with respect to the specialized distribution, like we defined in the experiment. So we define intermediate experiments for each level of the branching program, where we can only access LWE samples according to the secrets, the partial secret. Yeah. So we first apply it from the beginning to end. And only then we end up with the experiment that I described earlier. And then we can start to tackle each sequence individually. Yeah, so that's the last slide. So if you have more questions, now is a good time.
So you go back a slide, but that's not so. Are you using the assumption like small matrices, or these like how the experiment you gave, the adversary sees ICP in very different X. I guess I'm trying to match the querying and the oracle aspect of the experiment with the assumption. So is the like this is not the full assumption. You need to somehow change it to oracles.
Yeah, exactly. Yeah, the full assumption has an oracle, and then each matrix here actually has some index attached to it, and the adversary sends an index and receives an LWE with respect to the matrix that corresponds to this index.
So there's like an exponential number of A matrices and B matrices.
Yes, true. But I assume that he can only access a polynomial number of them if he runs in polynomial time. This is equivalent like him computing a partial path and then querying the intermediate value that he would get computing it.
And you kind of assume these exponential number of matrices can be like arbitrary. They don't have to have some specific description or something like that. It can just be arbitrary exponential A's, arbitrary exponential B's.
I mean, they do have succinct description because they depend only on the matrices of the branching
The
program.
way you use this assumption. But in the assumption you say, even if they didn't, it should be okay.
True, true. In that, yeah.
So these exponential number of matrices is what again, like the partial subset products, the partial subset products of S times B, I suppose, something like that.
Yeah, but in the intermediate steps, it won't be B because it won't be the output matrix. It will be some intermediate matrix of the branching program. So we go back to like a drawing of, yeah. So it will be like up until to this point, like all of the possible prefixes of x's and these public matrices.
Right.
Yeah. So that's it.
Time for some questions.